Imagine you gave Einstein AI in 1914, before he came out with the theory of general relativity. And you said, here's the data, here's the orbit of the planet Mercury. Can it predict that you need to go from vectorized data into Riemannian curvature? It's such a leap of human intuition. And I almost know that it couldn't do it because we tried to do it.
In this episode, Mike, Misha, and Xinghui visit Dr. Brian Keating, cosmologist, podcaster, and professor at UC San Diego. They discuss the cutting-edge instruments he helped develop to measure the faint polarization of the cosmic microwave background. Brian waxes poetically about taking inspiration from Galileo and building telescopes in the high peaks of Chile. He also walks the team through some of the techniques and assumptions that allow astronomers to look up at the sky and deduce the makeup of our universe. Please enjoy this conversation with Dr. Brian Keating.
Like, to start off the conversation, on the more celestial note, what's your favorite object in the night sky, and what does it mean to you?
Well, I would have to say the moon. The moon is probably my favorite object in the night sky. And it was really the first thing I ever saw as a kid and wondered about, and got attracted to astronomy because of it. And when I got my first telescope, of course, the first thing you want to look after it. And it actually drew me to eventually end up at the South Pole, where during the summertime at the South Pole, there's only two objects you can see that are astronomical. And so people wonder, why do we go to the South Pole to do science and astronomy when you can't even see more than two objects? But one of them is the moon. And even in the wintertime, you can see the moon. You can't see the sun. So the moon is the only celestial object always visible at all times of the year from the South Pole. So it has this unique distinction. And it's always been the most fascinating object to me. I want to go to the moon, visit the moon, mine the moon, and get some minerals there. Maybe live on the moon someday. So it's quite always been quite mesmerizing, I would say, in every way possible.
Are there any special features of the moon you particularly enjoy looking at?
Yes, there is a crater. I believe it's Copernicus crater, and it was sketched by Galileo through the telescope. And his sketches of it are beautiful. They're very artistic, but they're completely scientifically inaccurate. And Galileo is my hero, biggest hero I remember having science, completely followed his flaws and foibles, but he was an amazing scientist. And he knew how to do data science before we do. So he wasn't depicting the way that the craters actually looked, or the mountains in the way that they actually looked. He was depicting how it felt when he saw them. In other words, what was the visual sensation of looking at this giant crater that's on the meridian, the prime meridian of the moon as we see it? And he sketched it as he saw it. And, today we look at it and realize that he made these sketches, 400 plus years ago in Sidereus Nuncius. And we're still using them, debating them, thinking about them, trying to learn more about what he saw, why he saw it, and how it changed the course of human history more than almost any other discovery, observation, or invention.
When we look at the moon, why did people originally figure out where it was and what it was? Like, what's the rigorous proof? We're told in school that the moon is a satellite of the Earth. What's the rigorous proof of that?
Yes. So I like to always, ask my students if they can prove that I tell them the Earth is flat, and you will fail unless you can disprove me in the cosmology class. And I'd say, well, they can prove it, but a lot of them can. Almost none of them can prove that the sun is not the center of the solar system, or is the center. I say it is and it's not the center. I say, prove me wrong. I say, prove the Earth is not the center of the solar system. So all these things, I would say 0.1% of the human population can prove that the Earth is orbiting around the sun, not the other way around. Because that's the way it looks, right? Earth looks flat. Earth looks like it's being orbited by the sun, or the other way around. And certainly the moon orbits around the sun, so why not the sun? The moon orbits around the Earth, so why not the sun orbiting around the Earth too? So what is most surprising there? How do we know of that? It comes down to geometry. So the link between geometry, which is the study of math, but actually the geo in geometry means Earth. So the study of the Earth led to the study of mathematics that we now associate with geometry, and then, of course, higher geometry like general relativistic geometry, even higher dimensional gravity objects like string theoretic things, membrane theory. Those all come from geometry, which is measurement of Earth. So the measurement of the Earth led to the notion that the Earth is a sphere, or very close to a sphere. It's not a perfect sphere, but it's very close to it. And then going at different distances on the Earth's surface allowed us to make measurements of the distance to the moon. But not only that, Galileo actually estimated the height of the mountains on the moon, which is very crucial, through a telescope from the shadows that were cast at different times during the lunar year, which is the Earth month. one complete revolution around its illuminating, or the body that it orbits around is called its year, or synodic period, which is the moon's orbit up here. So he was able to measure the height of the mountains to within a few kilometers of what their actual value is, just with a crude telescope that's no bigger than the lens on a camera, a DSLR camera. So this is incredible that he was able to do that. And then once we go to different places on Earth, the parallax effect allows you to show that the distance that it is away and where it is on Earth. And that's actually how we mapped out all the different geometries of our solar system.
But so this is like the original assumption is that space is this three-dimensional Euclidean thing that happens here in front of us and also at the moon. Yes, otherwise, having never been to the moon, they have to make that assumption.
Right. So a lot of the early prehistoric notions of the geometry of space-time, as you might say, came from incorrect assumptions that had some kernel of truth. So Aristotle, for example, felt that heavy things fall faster than light things. So if I take this, very nice swag mug with the logo pointing your way, I won't show you my swag. I take this real Nobel Prize medallion that I got from Ray Weiss.
Oh, really?
Yeah. So these are much lighter, even though this is made of solid gold. And so if I dropped them, they would go at different rates. But Galileo said, "You idiot! Aristotle, just put one on top of the other, and he could prove that they fall at the exact same rate." But he had a kernel of truth. They're all attracted at the Earth's center. So once you had a radial direction, that started to map out that there are different positions in space in the third dimension, which we can't see. We don't see depth. So we look at the Andromeda galaxy, it's 6 times bigger than the full moon's diameter. So things width determines the proximity to us. We'd say, oh, it's got to be 6 to 12 times closer than the moon is, but it's actually 2.3 million light years away from the Earth, not 250,000 miles away from the Earth, light seconds, 1.25 light second. So Galileo kind of started to disabuse people of the notion of the Earth being the center, but there was always a notion of 3 dimensions. That you can go places on land, you could go places by sea, you could go at great distances. And if you had a tall enough, tower, that you would see things farther and farther away. And that's another thing that Galileo did. He didn't invent the telescope. Actually, Dutch invented the telescope. And they had access to the finest crystal, and they were traders. So they used their merchant economy, capitalism, capitalism is one of the best inventions on Earth. And I'm just joking. Capitalism led them to be not only a military power, but an economic power, which led them to be a scientific power. So what they were able to do is collect the best glass on Earth and make the best ingredients for telescopes. They never thought, though, to take the telescope and point it up at the sky. Galileo did that first. He made pictures of it, and then he started to discover you could see things farther away with a telescope. You could see things on the moon that imply that the moon must be extremely far away. And then they measured it over the year. Actually, they knew the distance of the moon before Galileo to within a couple of 1,000 miles. That was pretty good.
So the spyglasses were before that, right? For like checkpoint purposes, and then it was the one who figured out to look at it.
Spinoza was grinding glass.
That's right. Yeah, Spinoza was a lens maker by day, and then he was a heretic by night, and he was kicked out of the synagogue and kind of banished. But then he lived to his life influenced Einstein to have a notion of this kind of pantheistic God that Einstein later championed. So Spinoza's God. Yeah, exactly. Spinoza. So the Dutch had that, and it was known for a long time that the Earth was kind of either the center of the universe or it was in the universe, but it wasn't like there were just some dome affixed to which were stars, planets, and other objects that they didn't know much about, like comets and but the actual amount of depth perception they had was minimal. Even Galileo, as brilliant as he was, he thought comets were in the Earth's atmosphere. In other words, he thought they were atmospheric phenomena, like the meteorites that I gave you, and I'll give to you out there. Edu email address, I give these away, briankeating.com/edu, and you'll get an actual meteorite. And those are a phenomena that are in the atmosphere. They come from asteroids, fragments of them, burn up in the atmosphere. Galileo said, well, a comet's just like a really slow-moving meteorite. But of course, they're not. They're in the solar system, much farther away than the orbit of the moon. That was also discovered by trigonometry and what's called parallax. So, yeah, that's how we start to map out where our position is in the universe.
Do you have a favorite answer for why, or proof for why the Earth isn't that? Like, has any one of your students ever written something that's actually really original?
Not about why the Earth is not flat. I think they're all comfortable with that. They can kind of figure that out on their own. And that was done really since that day, like 2,500 years ago, Aristotle. But proving the Earth is in motion was not proven until the late 1700s, early 1800s, when they noticed it was called parallax or stellar aberration, rather. So if you look at a very distant star as the Earth goes around the orbit with respect to a very, very distant star, you'll see that trace of the pattern of the star will map out a little ellipse or circle. And that's indicative of the fact that we're orbiting around the sun. There's a slight parallax shift between us and that star, even though the stars are running huge distances from us. Even the Earth's orbit, the orbital distance between 93 million miles, 186 million miles across, that's enough to get enough parallax to see that stars will make a little circle as we roll into the water. Well, it's right next to the stars. More distant.
Even more.
Yes, yeah. So closest star, approximate Centauri, is 4 light years away. Look at something that's 10 light years away. That'll be almost exact. It'll have half the parallax or less. So you'll be able to see its motion as kind of a cosmic wallpaper beyond what you can see. Things moving in relative motion. People knew that for a long time. But it took a lot of thought to think about that, because it's actually, it wouldn't be, the effect is made more prominent by the speed of the Earth's orbit being a fraction of the speed of light. If it was much, much slower or much, much faster, you'd have different results. It'd be harder to prove that we're in motion. So most people get that wrong. But I don't use it for final exam.
So did you have a telescope as a teenager? Is that how you go fast?
I did, yeah. So one night I was asleep and I woke up and I saw the moon was out and it looked brighter than any light I'd ever seen. But next to it, it looked like someone had broken a piece of the moon off, because there was a chunk of light, or bright spot of light that was the same intensity, per given area, kind of intensity of light. But it was obviously like a star. I thought it was a star. And this is in 1985 or 1986. So it's not like, I'm going to ask ChatGPT about that. No, Halley Collins really did. But that was around the same time. So I was too lazy to wait for Google to be invented 16 years later. So I decided to do some research. I went to the library, got the New York Times. Back then, they used to have a section where they'd plot out, called the cosmos. What's that in the night sky? So it showed the moon's position. And then next to the moon that night, or the night before, it showed Jupiter. What the heck? You could see a planet with your eye. I thought, it was just around the time Voyager was making its rounds around the solar system. And I just was blown away. And I was like, if I could see that with my naked eye, imagine you can see with a telescope. So I had a job at the time working in the Venice deli, which is kind of funny because Galileo would get money from the Venice Senate. I got money from the Venice deli, and I was shocked, the 3-letter agency known as the MOM Foundation. My mom kind of doubled my $2 an hour income. And I was able to buy a telescope after, kind of 3 or 4 months of scrimping and saving. Got the telescope, and, for me, it was like using the whole telescope was launched, but it would have been like the biggest telescope on Earth. I could do whatever I wanted with it. And I just kept ever increasing the size of the telescopes. And now we have a 6-meter diameter telescope in Chile in the Simons Observatory. So a million times more collecting area than my first one.
When did you build your first telescope, or were you involved?
I recently built it. So an optical telescope. Recently built one. And my kid convinced me to get my oldest guy convinced me to buy him a 3D printer, and he 3D printed. And we got we bought a lens from Edmund Scientific and a focuser from China somewhere. And 3 months later, he printed out this beautiful telescope. I'm actually going to bring it in. It doesn't work that well, but I'll tell him that. He used wood screws instead of metal screws to put it together, but it's not working that great. But anyway, he'll find out when he sees this video. Where I put it. I think it'll admit right. So that was my first optical telescope that I ever built. Kind of player. But I've been building, for my research, which is not using optical light at all. It's using microwave light. I've been building telescopes for 25, 30 years since graduate school. So our telescopes don't see visible light at all. We could put it, in the middle of, the Sahara Desert at high noon, and it would work, just fine, basically. But instead, we do put in places like the South Pole or Chile, where not the light pollution, yes, the light pollution is low, but the heat pollution is what we care about. So we want to be somewhere cold because we're looking for this faint signal from the Big Bang's origin.
So why did you decide to focus on microwave part of the spectrum?
Yeah, I kind of fell into it. When I went to graduate school, I was a graduate school student at Brown, and I wanted to be like a theorist and study condensed matter physics. And I never really thought back to, I loved astronomy when I was a kid. Why didn't I do astronomy? It always seemed like being, an ice cream taster or something. No one's going to pay you to use a telescope. But I realized that you could build your telescope, then you're the first and only person that knows how to use it. So I could use that as kind of an unfair advantage to build, to kind of build a brand around what I wanted to study. And that was building experiments that blended physics, low temperature physics, cryogenics, to cool sensors down to near absolute zero, 3 Kelvin or below, and build those detectors to do a study of what's called polarization, so the least familiar property in light. You got spectrum, you mentioned that, its intensity, how bright it is, its color, how when the spectrum, but its polarization is what orientation the electromagnetic field vectors are oscillating. That was not studied in the CMB. It was not detected in the CMB when I started graduate school in the early 90s. So that was a kind of like blue ocean. I could do something no one had ever done before. I worked with a great advisor, still one of my closest friends, Peter Timby. And he was just a great mentor. And I would say to my students, it's more important who your advisor is than what he or she studies, because you're going to have a relationship with them. I mean, he came to I've known him longer than I knew my wife. I've known him for 30 plus years now. And he's seen me at, my dumbest. And now he's seen me, with my success. And so it's more the person that I want to work with rather than the topic that I want to work with. But happily, I fell into a great field that has had nothing but high energy growth for the last 30 years, which is quite exciting.
Was cosmology like a hot area? Like today, a hot area is like AI, right? Or something like that. Was cosmology AI for physicists at the time you got into it?
Yeah, cosmology was kind of just going from being a laughingstock to now being respectable. So the COBE satellite was the first major US satellite that was launched in late 1980s. And in 1992, the year before I went to graduate school, it returned the first hard evidence that the universe was a perfect black body, that the spectrum of heat from the Big Bang exactly matched the predictions that would be present in an expanding universe that started off in a big bit. That had been known to measure since Penzias-Wilson, at least at spots along the spectrum, but it took actual satellite mission to measure it over the entirety of the electromagnetic spectrum and to get it down to the sub-millikelvin level of precision for the first time. So it did that, but it also measured that there were deviations from perfect isotropy. So the beach ball, then I go all down there, and beach ball, there's one. So it's over here, okay. So hopefully you can see it in the camera. So these fluctuations in the zone, so these fluctuations in the microwave background, if you're watching, you guys do audio only too, right? Yeah,
We do.
you should. You get the big mic, big sponsorship. These fluctuations are indicative of the early universe's first light, the properties of the very first photons that were able to propagate freely in the universe since the Big Bang itself. So this is a snapshot of what hydrogen and dark matter effectively looked like in the early universe 380,000 years after the Big Bang. What COBE did in 1992, the year before I went to graduate school, is measure these large-scale fluctuations, not these tiny little ones, but these really big splotches where you have all blue, all red and green over there. So that was the first time that we discovered that the universe had an amount of what's called anisotropy or inhomogeneity that deviated from perfect isotropy. We knew that we exist, so there has to be some part of the universe that was broken into fragments and had a place where matter could accumulate. And what we didn't know what those values were. No one could ever measure them until COBE measured them. And COBE was designed and turned out and built in part by Bob Dickey, who was a very famous astronomer at Princeton, and had done work in World War II at the MIT Radiation Laboratory working on radar. So along with the Manhattan Project was an equal and in some ways more important work on radar that was done mostly in the US and Britain. And almost nobody knows about it. So, there should be an Oppenheimer, maybe there'll be a Dickey or something, I don't know. But there's an incredible project. And through that, we had developed very sensitive detectors for measuring microwaves, radar waves, which is in the microwave range, and the radio spectrum. So what they invented, and my grand advisor, my Peter Timby's advisor, Dan Wilkinson, they had invented these types of switching radiometers that could very exquisitely measure the difference, not the absolute temperature, but the difference between temperature over there and temperature under here. And by comparing those at every single pair of points that you could know in the sky, it was just phenomenal. So it was a very exciting time, like you're saying, kind of the way AI is now, but in the physical world, you could actually build stuff. It wasn't coding,
maybe like robotics or something now is getting like that. But to actually do something with your hands, which I love to do observations and to build stuff that no one had ever done before. They had measured the spectrum, they had measured the isotropy now, but no one had measured the polarization. And we thought, we could try and do it.
So why no one measured polarization before? What was the challenge?
Yeah, so polarization is really faint. So if you're watching, you can see on top of the book cover, that lovely book cover, Losing the Nobel Prize, there's this glare from the lights. Now, if you had polarized sunglasses, which, we have to wear here in La Jolla and San Diego, you could actually remove the glare. The glare is coming from the fact that unpolarized light is bouncing off of matter, and it becomes partially polarized. But the amount of fractional polarization that takes place is about half to 1%. So actually, that's actually quite bright. Compared to the CMB, it's orders of magnitude more highly polarized than the CMB is. So the answer is it's very technically challenging to measure polarization, but even more so when the signal itself is close to absolute zero, and you're measuring a fraction of a part in a billion or tens of parts per billion of that signal that's partially polarized. It won't be 100%, but it'll be partially polarized. So it was just a technical challenge. Jacobi tried to do it. They just couldn't measure it. They got an upper limit on it. And we decided we actually ended up using the same exact feed horn technology and so forth that they had just gotten as a gift from my grand advisor to my advisor. And that was part of my PhD thesis experiment.
Maybe if you can explain a little bit more to the audience how to perform like polarimetry or measurement of the polarization. How's it done?
Yeah, so polarimetry is the study of polarization. It involves looking for the asymmetry between the plane of oscillation of the electromagnetic field. So electromagnetic waves propagate at the speed of light, and they have three properties: their wavelength or frequency, their intensity, their amplitude, and their oscillation direction, because they're vectors. The vector in which the electric field oscillates is called polarization. Perpendicular is a magnetic field. We don't usually see magnetic polarization, but it's there. When you have an unpolarized light source, it's like two people holding a rope and causing it to oscillate in all different directions. So unpolarized light, like from the sun or from a black body, is 100% unpolarized or 0% polarized. But when light interacts with matter, see, that's unpolarized light interacting with matter, scattering off the book, it suppresses one of the two directions of polarization, meaning that the part that's vertical, perpendicular to the surface, gets absorbed, and the part that's parallel to the surface gets reflected. So what you do with polarized sunglasses is you have an orthogonal direction, you suppress that direction, and now you can see past that surface of reflection. That's mostly useful on water, or cameras use these things. They're called neutral density filters.
The glare.
The glare, yeah. So you can see through glare on the ocean surface with them. Or you cut down on the total intensity going into your eyes so you don't fry your eyes and you see more detail and more perspective. That's polarization of optical light. But all light sources have this.
Is there any like intuition? I mean, I could derive it from Maxwell's equation, but intuition for the glare, why it should be of specific...
Glare is just what we call the additional, the lack of suppression of one of the two polarizations. So it's like a mirror. It's just like a partial transmitting mirror, partially reflecting mirror. And it's reflecting one of the two polarization states more than the other one. At certain angles, you'll get complete internal reflection. That's what Brewster's angle is. Fiber optics, lasers will be completely suppressing that, the polarization direction internally, so it'll reflect completely internally. And so the glare is basically just the same color, intensity, and so forth as the unpolarized light itself. It's just you're seeing it, and now you want to suppress that because it's basically interfering. If you're looking into a water surface, you don't want to see the sunlight. You want to see what's in the water. So you want to suppress all the reflected light. But if you suppress all the reflected light, you'll have nothing to see. So you're basically throwing away half the light in order to see with the other half the light with more clarity.
And was there a specific technological trick or piece of equipment that you guys used that made you be able to measure polarization more clearly?
At that time, the technology that we used was called were types of transistors that could be cooled close to below the temperature of liquid nitrogen or around them below, and still operate and still conduct. Usually when you cool transistors down, you freeze the electrons. They're not going to be very good conductors. So you won't be able to have much gain from a transistor amplifier. So what you do is you have like a horn that points at the sky. You want that microwave energy to come in. You want to amplify it. You maybe want to get its spectrum as well. What are the wavelengths that are coming in? And then you want to have do that when you have a lot of background noise. We're looking for a 3 degree Kelvin signal, and we're living on a 300 Kelvin planet. And the amount of black body energy scales as the fourth power. So you've got 100 to the fourth power more energy.
Stefan's law.
Yeah, so it's Stefan's law, exactly. So it's just astronomically larger amounts that would dwarf it. So you want to have a very narrow frequency range. So these transistors had recently been invented by teams at NIST primarily for communications and in the exact frequency range that would be useful for us to study the CMB. Nowadays, nobody uses those amplifiers. That's what's called coherent detection, like in a laser or whatever. Coherent means you preserve the phase, wavelength, and all the other properties of the wave. We did that too. Nowadays, we use what are called bolometers, which are phase insensitive. They actually destroy the phase information. They're just total energy detectors. So how much total heat is coming from a given pixel, it will then heat up a tiny little superconductor, and it will change its resistance, trying to get it to not superconduct anymore. And then we measure how much cooling power we need to supply to keep it superconducting, and that gives us how much microwave energy is trying to heat it up, which is a minuscule amount. We're talking picowatts of energy from the CMB. And you do that the last thing I'll say, you have to do that for each polarization state. There's just two polarization states, either horizontal and vertical, or left circular and right circular. And you need an amplifier for each one of those, or some combined splitter that takes those apart. So we use the splitter back for my PhD. And now we have a separate detector for each one of the polarization states. But you also have to do it for every frequency in which you could have an astronomical signal, whether it's cosmological or whether it's from the galaxy, which is what my first book is about.
So yeah, it sounds like a completely different like paradigm from optics, like what Galileo would use, like lenses, a stack of lenses. Like here, your molecular electronic side, like maybe this antenna arrays.
Yeah, we do use antennas, but we do use lenses. Both of the telescopes, BiCEP is a refracting telescope. It's only about 25 centimeters across the primary objective lens. And then the Simons Observatory uses a much bigger one that's about a half a meter across.
Is it lens or mirrors?
Lens. So these are the ones that look for. So you only want to. I learned this.
What's the best lens material for microwaves?
So you guys are asking all the right questions, but you're asking them all at once. So I have to multiplex my answers here. I'll do sign language to Mikhail. So let me start with the first one. So you asked how big are the lenses? Why are we using? So I said we have one 6-meter telescope. That's a mirror telescope. That one's it's not looking for gravitational waves. For gravitational waves, you only want to build a telescope that's just big enough to do the science that you care about, right? So if you wanted to look at the full moon, and that's all you cared about, you don't need the James Webb Space. You don't need a 6-meter or the 30-meter telescope that Caltech and UCSD are building, right? UC is building. That's a total overkill. For gravitational waves, the signal in the sky will be which determines the resolution. The angular diameter of the signal determines how big a resolution, how big an aperture you need, and the aperture determines how small a feature you can see. So you only want to build a telescope as big as possible just to detect what you want to see, but no bigger, because that's just adding extra expense. The cost of a telescope goes as the third power of the diameter of the telescope. So it's kind of like the volume goes up, the resolution only goes as the first power. So the angular diameter that you can resolve is just the diameter of the telescope. So the smallest feature, the smallest crater you can see on the moon that Galileo could see was limited by how big his aperture was. But beyond a certain range, I mean, he's not looking for like the footprints from the astronauts on the moon. Allegedly, no, they were there. That's one of my favorite things. People claim the moon landing never happened. I have to argue with them online. So the telescope size is built to just accommodate that size. So we use a refracting telescope rather than a reflecting telescope. The refractor diameter only has to be about 8 inches to 20 inches or so in diameter. So for the Simons Observatory, the BiCEP was about 8 to 12 inches in diameter. For the Simons Observatory, it's a half a meter in size, roughly. And the different materials that we use, to answer Mike's question, we use basically a plastic that's very low loss in the microwave region, but it's completely opaque in the visible. So it's just called ultra high molecular weight polyethylene. It's the same material that they used to make milk jug containers out of, but now environmentalists made it.
Is it possible to 3D print it? Maybe that kind of mirrors.
Yeah, people have done that. The problem is you get structures on the scale of the wavelength for a 3D printer, but we've tried. We've thought about it. And it's not that hard to get that kind of plastic. That plastic's a little more lossy. So now we use basically alumina, which is synthetic sapphire. It's very high purity, but you can't see through it with your eyes, but microwaves go right through it. And you can make it really big. The problem is, just like if you look at your iPhone there, see how you can see reflections off of it, or if people wear glasses. there's reflections off of every dielectric surface interface. But we want the light to get in. We don't want it to reflect out. But we also have to keep the thing under vacuum, unlike your iPhone, and we have to cool it down to 0.1 degree Kelvin. So 100 milledegrees Kelvin using what's called a dilution refrigerator. We can talk about that. And so effectively, imagine trying to get your iPhone to work at, even below zero is not guaranteed. But also to keep reflections out, to allow radiation to get in, but not contamination to get in, to do it at all different frequencies, all different polarizations, with 100,000 detectors total across the whole observatory, and collect data and analyze the data and condition the data and treat and process it. It's a huge effort. So there's 350 people working on the project.
Do you do like a frequency sweep, like just in the radio, or you try to get all the?
We don't have to do that. So a bolometer, unlike a coherent amplifier transistor, bolometer takes in all the frequencies and basically asks how much energy is in that. It's kind of like if you go outside with your hand on a sunny day here, and you put your hand around, you could find roughly where the sun is from the infrared heat that warms up your skin. And the same thing could happen with these detectors. You couldn't do any frequency resolution with it, but you don't really care. Let's say, whatever, you're blind, you're trying to find the sun. You don't care. We don't care about the actual frequency coverage. We just care we get enough photons that we get a signal-to-noise ratio that's much bigger than the background, which is coming from the Earth, the atmosphere, and the galaxy.
So there's a lot of different technologies that you need to use to build these telescopes. Did you just learn everything on the go as you did your PhD, or did you learn this already?
Well, the first thing to realize is that nobody does it by themselves. Like everything I'm talking about is tens to hundreds of people throughout my whole career. And certainly now, the size of the telescope and the size of the collaboration just means more and more people that are much smarter than me are needed to make this thing actually work. So that's the first thing. A lot of it is kind of just-in-time learning. Like if you just read all these books I have here, for no reason, who knows if you'll ever use any of it, but it's certainly not an efficient way to learn something. So when I was doing stuff with the coherent amplification, these transistors that are very sensitive, I had to learn about them and how to build circuits like that. That knowledge was basically useless when I started working at Caltech as a postdoc and working on bolometric detectors, which are completely different. They're basically just thermometers attached to absorbers, like I said, like your hand. And then those just get more and more complicated. They're very difficult to make. They're made photolithographically. They're not... they're microscopic. They're really small. They do everything, like frequency filter, polarization filter. They don't amplify. They don't do anything to the signal itself. They have no frequency resolution, but they're incredibly sensitive. They can detect, literally like a pretty bright light at the distance of the moon. These things, in terms of their power, raw power sensitivity, they could detect. And we have literally 100,000 of them. They're built and designed by my colleague Suzanne Staggs at Princeton, and NIST in Colorado, where they're fabricated. And these are just phenomenal objects in large part because they're superconductors. So you have to make these out of superconductors, and superconductors are really finicky, difficult to lithograph, to make them work sensitive, and then to get the signals out of a pure vacuum, an almost total vacuum. It's a millionth of the pressure we feel here. And then to deploy them and have them at the right optical properties. This is decades of people work, that have gone into this. So it's really complicated. And I just try and, kind of stay, apace with what they're doing. And my main focus is literally, trying to make sure everything comes together at the right time, that the people are in the right place, logistical, and that we're funded, and kind of the big picture, coming up with the idea for building it with colleagues and seeing it through to publications and getting the results out is the most exciting thing, but it also takes a really long time.
So I guess obtaining the funding is a big part of the work now. What are the typical funding sources? So
for BiCEP, it was funded purely by the National Science Foundation, more or less. There were a couple of private grants. And the exact opposite for the Simons Observatory. It's 100% funded by the Simons Foundation in New York City, and member institutions like UCSD and our colleague partners and colleagues around the world. Like there's 45 or 50 different institutions, 300 plus people. Everybody contributes intellectually, and some also contribute intellectually and financially. But 80 million so far has come from the Simons Foundation alone. And by the time it's done, if we're getting an upgrade to it, and we'll talk about that some other time, but it will be close to $200 million project. And the large majority of that will come from the Simons Foundation, but not all. And hopefully we'll get 25, 30% from the National Science Foundation.
So a lot of the idea of searching for, let's say, I mean, this is a big topic of your book about losing the Nobel Prize. A lot of the idea of searching for, let's say, evidence of inflation is predicated on, assuming the Big Bang, right? How sure are we about the Big Bang? Like, is there a cosmic dust equivalent of like something that might be causing us to think there was a Big Bang when there really wasn't?
So for every theory, there's always a counterpoint. There's always somebody who doesn't believe in the theory, who will make their career, based on the quest to disprove the prevailing theory, to show that they're all idiots and that only they know the truth. And
It's called Newton's third law.
I think it's Clarke's law. Clarke said for every expert, there's an equal and opposite expert. And he's the namesake. He gave us the namesake of the podcast. So to answer your question, there are, I like to joke, there are members of the Flat Earth Society all over the globe, right? So there are people that believe it everywhere, right? There are people that don't believe the moon landing occurred. There are people that don't believe in evolution via natural selection and chromosomal heredity. All sorts of things. People have belief in their own theory, or they believe that the prevailing wisdom is a conspiracy. For what reason? At least for the moon landing, you could kind of see there's a conspiracy. I'm not justifying it, but NASA, is embarrassed because they said they could do it, and JFK, pushed the country to do it as a big source of national pride. We want to beat those nasty Soviets and Russians and whatever, and so they lied about it. But that's total nonsense. I mean, it could prove that it happened. Colleagues of mine here have studied not only the moon, but measured the position to the moon to better than a millimeter using lasers shot at the moon. From New Mexico, and they're reflecting off of the very exact reflectors that were left by the astronauts that they have pictures of themselves putting there. And it's known not only by the U.S., but by every country that does this type of metrology to measure things in the solar system and the universe. So it's a total joke. But at least you can see how people do. The Big Bang opponents that deny, I call them Big Bang deniers, liar, liar, Big Bang denier. I do videos about these people. They're really buffoons. They, in some cases, have... They have ulterior motives that they are, in some cases, one guy is trying to build a very low energy neutron mediated fusion reactor in Pennsylvania somewhere. And he's always getting people to give donations. And the way that he does it, he makes a big case that the Big Bang never happened, and that all of cosmology is a sham and a scam. It never happened. But actually, in this very office, the previous occupant of this office was named Jeffrey Burbidge. And he was an amazing astronomer, cosmologist, and he never believed in the Big Bang. And he was here for a very long time. The guy who came up with the name Big Bang, Fred Hoyle, didn't believe in the Big Bang. They believed in what's called the steady state universe, that the universe always existed and always would exist, and it was changing slowly. And the way that it got the behavior where we saw galaxies moving away is that there were pieces of helium and hydrogen that were created every year in the universe and only need a tiny amount to cause the universe to expand. So they went to their graves thinking that the Big Bang never happened. They didn't have the kind of violent antipathy that these other people do for some reason, that are really obsessed and hate things like the James Webb Space Telescope and hate NASA and hate cosmologists like me. But they were pretty vehement. So the answer is because no theory is perfect. Even the theory, so if the flat earthers said the following, if they said the Earth is not a sphere, I would agree with them. The Earth is not a sphere. The Earth is what's called an oblate spheroid. It has a distortion because it was once molten and it's bulging at the equator, like some of us do as we get older, because it's rotating. So it has deviations in the spherical harmonics that are along the midplane of the Earth, and there are other deviations too. Plus Mount Everest and here in California we've got Death Valley. So there are variations. So it's not a perfect sphere. So that would be right, but they don't say that. They say the Earth is flat. So they make a concrete claim with high precision. They say the curvature of the Earth is 0.0000, and we know we can roll that out at infinite sigma, an infinite number of standard deviations. We can say that the Earth is spherical to within so many standard deviations, and we can say what the deviations are. We can account for those very accurately, but at the end of the day, we can never prove a scientific fact. Karl Popper said you can never prove something in science the way you can in math. You can prove 1 + 1 = 2, which is another thing people dispute online. I'm in a debate with this guy, Terrence Howard, about 1 × 1 = 2. He claims that. And he's a brilliant, actor and everything else. But I said, if they gave you one paycheck for $1 million, and then they gave you another paycheck for $1 million, would that not be $2 million, or would you expect
I would
more?
want to do business with him.
Right, exactly, right. So at the end of the day, there'll always be detractors, doubters, and so forth, but the onus is on them once you have enough preponderance of evidence to support a scientific claim. So we have really 3 or 4 different pieces of evidence that point to what we call the Big Bang. If you say the Big Bang is the origin of time, that's where we can start debating if that's true. But the Big Bang theory is really referring to the formation of the earliest elements, the lightest elements on the periodic table of the elements. I got a chart behind you over there, and the formation of the cosmic microwave background, the formation of the first stars, the first galaxies, first clusters of galaxies, and everything else that goes into them. And people always say, well, how can you guys talk about the Big Bang with such confidence if you don't know what 95% of the universe is made up of? We don't know what that's true. We don't know what dark energy is, and we don't know what dark matter is. We've never detected a particle of dark matter. We've never detected a quantum of dark energy. And lately it's been as exciting as I can remember it's the second major paradigm shift that may be occurring. The first in my career, at least, was the discovery of the accelerated expansion of the universe in 1997. And then now, in the last year, there's evidence that the expansion of the universe is not caused by a cosmological constant. The acceleration is not caused by it, and may diminish and may eventually stop, perhaps. And so the cosmological constant has come under question. So that's a really exciting thing. None of that has to do with the other things that we test about the universe, namely the CMB. You can only have a CMB in a universe that once was hot, dense, and that's the context that we mean by the Big Bang. And you can go even further back that every hydrogen atom in your body and its isotopes were formed only during a very brief period, less than 20 minutes after perhaps the origin of our universe. We can't say what the origin was, but perhaps after the inflationary epoch ended, or perhaps after a previous universe collapsed to form our universe. There are people that seriously study that. But there's no way that you can have consistency with that if you don't have a hot, dense phase of the universe where you effectively had an extremely high energy density, extremely low entropy in the early universe, and then the expansion that comes out of it. You don't need dark energy for any of that. Dark energy only starts to play a role about 4 or 5 billion years after the Big Bang, 4 to 7 billion years after the Big Bang. Dark matter, same, hundreds of thousands of years or to millions of years after the Big Bang. You can get the CMB and dark and the formation of the elements only in the model that has a hot, dense phase, and that's the model we call the Big Bang. So these alternative models are just total nonsense. They don't predict the CMB, they don't predict the formation of the elements, they just pick at where there are uncertainties, disputes, and conflict and tension, but that's part of a healthy field. When everyone believes the same thing, like the Earth is flat, that's kind of the last stage of that before you descend into complete and utter madness.
And what's the strongest evidence for the Big Bang? Is it the expansion of the...
I said there's 3 main pillars of the Big Bang. So there's the formation of the lightest elements in the periodic table. That's called primordial nucleosynthesis.
If there wasn't like a hot moment, then those things would not have formed in the quantities that we see them.
Yeah, the universe was a fusion reactor. Mm-hmm. The universe was a fusion reactor at every point in space and time in the extremely early universe for the first 20 minutes. After the first 20 minutes, almost nothing happened. Nothing happens until the formation of the first atoms. So the relics, I always like to think of cosmology as kind of like archaeology. They're fossils that we can study. When I look at you, I'm not seeing you instantaneously, right? Light travels 1 foot per nanosecond. You're 2 feet away. I see you 2 nanoseconds ago. Okay, not a big deal. We see the sun. The sun could have disappeared right now. We wouldn't know about it for 8.2 minutes, right? Same with the nearest star. Nearest star could have exploded 2 years ago. We won't find out for another 2.3 years. However, if we look back to the very beginning, we have fewer and fewer kinds of artifacts, relics, fossils from that period. But in the case of the Big Bang, there are 2 extremely high precision measurements that we've done. One is the CMB. The CMB is the relic radiation, the oldest light in the universe, the oldest fossils in the form of light. What did it come from? The fusion of a proton with an electron. We don't normally call it that, but that's what it is. Binding, or it's another way to say fusion. The equations that govern that tell us that process could not have occurred before the universe had cooled off to below the ionization temperature of hydrogen, more or less. There's some corrections, but So too, the hydrogen and helium in this water and its isotopes, deuterium, and I have heavy water in my lab. I'll show it to you guys. Heavy water, the isotopes of hydrogen, they cannot form. There, it's a fusion process too. Deuterium is the simplest of all nuclei. It's discovered by Harold Urey, who was a professor here. That's a fusion of a neutron with a proton. That cannot happen before the universe is cooled below about 1 billion Kelvin. Okay, that took a few seconds after the Big Bang, and it lasts until there are no more neutrons. Neutrons are unstable; they radioactively decay and beta decay unless they're combined with a proton. We don't know why that's true, but it is true. They'll decay after 880 seconds, and so if you don't make anything that needs neutrons, namely every other element on the periodic table has a neutron in, except for hydrogen, the isotope that we call protium. Everything else has a neutron. So all the neutrons that were produced in the Big Bang are bound up into the periodic table or bound up into things that were made in the Big Bang itself. That's a fossil. So that means you go down to the ocean, you scoop up some water, you say how much deuterium is in there. That will tell you exactly what the ratio was like, because you don't make deuterium anywhere else except for the Big Bang. So you often hear, oh, we're star stuff. Carl Sagan, we're star stuff. We're made of star. No, we're mostly made of hydrogen, and all the hydrogen was made during the Big Bang. So that's what we should think about. So it's the formation of the CMB, and it's the expansion of galaxies in the universe. Those three things point to a earlier, denser, hotter, a higher entropy state, at least in a higher energy state in the early universe. How that started is an open question. That's what we're trying to study.
And you were just talking about dark matter and dark energy. Is that something that you are actively interested in researching? Because I saw this year you had an archive paper on ALPS, like axion-like particles and birefringence. Is that something you can also detect, or is this a new direction? Yeah, no, it is a new direction. So part of the interest in the CMB is because it is the oldest light in the universe. That means anything that we interact with, or anything that's interact with light that you'd ever want to see or could see, you can't see that event before the formation of the CMB. The universe was a pure plasma, and in plasma, light doesn't propagate freely. It gets scattered. It's like the sun is a plasma. You can't see into the sun. There's too much scattering. But if in the early universe, all we had was protons, neutrons that were bound with other protons, and electrons and heat, until the universe expanded enough and cooled enough that you could see from the last scattering event that ever occurred for those photons to today. So that light came straight to, that's what this globe is. It's a picture, as God would see it outside of our universe, of what the different temperatures of photons would be as they were at the surface, when the surface was comprised of dark matter, ordinary matter, and photons. We see that light, it comes to us. It tells us about all the events that occurred before then. So it's the longest leverage that you could ever have on phenomena that involve light or propagate at the speed of light. Gravitational waves also propagate at the speed of light, as you know. And they do imprint the CMB with a specific type of pattern that we are hoping to see. But not only that, any type of matter will interact, and just as that glare showed us before, when light interacts with matter, it develops polarization. It's called Thomson scattering. Thomson scattering can either tell you about the properties of the light or the properties of the matter. But if you know the properties of light, which we know very accurately is a black body, then the polarization tells us about the quantity or composition of the matter. So we can kind of reveal how much of that matter could be dark matter versus ordinary matter. And there are other more sophisticated ways to do that and to see that there could be a coupling that are highly speculative. We have no idea if this is true. We know for a fact that dark matter exists. We see it on every scale outside of the solar system. We see it in our galaxy, clusters of galaxies at the CMB, baryon acoustic oscillations. We see every single example of a gravitationally bound structure has dark matter, but we don't know what it is, so it's frustrating.
So in your book, you mentioned a lot about the stardust, or like in general, like maybe some nanoclusters are flying around, or something which it's difficult to see from the Earth. So could it be dark matter, something else what we're looking at? Or?
No, it can't be dark matter. So if you pick up that meteorite there in front of you is a giant chunk of dust. So the dust that kind of obscured our view of the CMB was ordinary matter in our galaxy. Dark matter doesn't interact with light. This matter does interact with light. So what happened with this matter, these tiny grains of micrometeorites basically from a detonated supernova that blew up 4 or 5 billion years ago in our galaxy, not in our solar system, in our galaxy, that made little particles basically of iron filings, like a compass needle. The galaxy has a magnetic field that then aligned those particles along a preferential direction, which made exactly the same type of pattern that the CMB would produce if gravitational waves are present. The only way to get rid of that is to go beyond the galaxy into intergalactic space, which is very expensive and difficult to do in these funding climate time that we live in. But it's ordinary matter. It's matter that interacts with light. So dark matter, its key characteristic is that it does not, you should really call it invisible matter. It's matter to which light is impervious to, kind of goes right through it. And there are examples of dark matter that are familiar to you. They're called neutrinos. Neutrinos do not interact with light. They go through ordinary matter, light years of ordinary matter without any chance of scattering. And they have mass. Neutrinos are known to have mass. So they have all the characteristics. The problem is they don't have enough mass, and there aren't enough of them to make up the preponderance of dark matter that we see through all these cosmological surveys and that we know exists, but we don't know exactly what it is. So people have proposed these other things, as you said, Shungwei, called axion-like particles, or ALPs. And these are particles that are kind of like heavy photons. And they reveal themselves in that they will cause the polarization state of the CMB to behave slightly differently than it would if they don't exist. And you can measure the product of their cross-section and their mass the same way a dark matter experiment would do them effectively. The more the mass that they have, they'll affect the dark matter. The clumping of dark matter will be affected the more massive they are on smaller scales. So you'll have more clumping at small scales, less clumping at large scales if they're heavy, and then the converse is true if they're light. These are very light particles. These are like 10 to the minus 27 electron volts or something. I mean, incomprehensibly massless, but there's so many of them, like there's so many photons that they could comprise the dark matter that we do perceive indirectly.
And can you reevaluate data from older observations to evaluate this, or do you need to build new, more sensitive or at different frequencies?
It's kind of like, could you take a picture? Could you make an Apple Vision Pro, with a camera, from 1999? You could, maybe it wouldn't be that good, and it certainly wouldn't have all the features and the resolution and the quality of it. And so one or two, because the field moves so fast and people can build detectors and we kind of are outpacing Moore's law in terms of the number of detectors, the sensitivity of the detectors, it just doesn't make sense to do that. Like in 1 year of data with the Simons Observatory, we can do everything that BiCEP did, in 3 to 6 years of observations and way more. I mean, we could do a lot more than that. And so it doesn't pay, although we are analyzing data from experiments that we've decommissioned at the same site in Chile, but different purposes. Also looking at polarization, but it wasn't originally designed to look for dark matter masses.
Maybe talking of BiCEP or the earlier projects, could we go back to the time when you worked on that, and what was the story behind it?
Yeah, so I was a postdoc at Stanford right after I got my PhD, and I went to work for a young assistant professor, and her name was Sarah Church. And she had been a postdoc at Caltech, where I would later end up after she fired me, which is not a career direction I recommend your listeners go off on, but that's what happened. I was working for her. She was working on like galaxy clusters, a little bit on polarization. I'd wanted to work only on polarization. And then I had this idea based on a paper by one of my future friends, Mark Kaminkowski and others, that you could look for gravitational waves using a very small telescope that wouldn't cost as much money, or cost a fraction of the big telescopes that were being planned for my field. And so I was obsessed with it. I kept thinking about it. How could you build it? What would it look like? What would it do? And she just noticed that I wasn't working very much for her anymore. And yes, she was paying me. Not that much, it was like 30 grand or something. And this is at the height of the first .com bubble. So imagine like the AI bubble that we're in now, but times like 1,000. And that was what the .com bubble was. These companies were, so to get a house near Silicon Valley for a postdoc on $30,000 a year salary before taxes was I was miserable. So I lived like on the train tracks essentially, and I was almost homeless. I hated it. It was awful. And she could tell, so she fired me one day. Won't get into the details of it, but she did me a great kindness. She sent me for a job appointment with her former postdoctoral advisor at Caltech, who was named Andrew Lang. And he was a really famous scientist. He had just finished measuring the very first observations of the fluctuations on the cosmic microwave background at small scales on this experiment called Boomerang. He was like this incredibly powerful, charismatic guy. He'd come up to Stanford to give lectures on these new discoveries. Everyone thought he was going to win a Nobel Prize. And he invited me to give a talk down at Caltech, a job interview. Went down there, he liked to talk, offered me a job. I said yes before he finished, the sentences coming out of his mouth. Moved down to Caltech, worked there for 3 years. And while I was there, I became friends with a postdoc or scientist that worked with him named Jamie Bach, who's now a very famous professor and PI of this new satellite called SphereX. And I convinced Jamie of this idea that I had at Stanford to build a small telescope, put it at the South Pole, and observe for 3 to 4 years and set some limit. And we didn't think we'd detect anything. And over time, we hired more and more people, and then we upgraded the instrument like your iPhone. Every year, it gets more pixels, better sensor, or whatever. So we improved it. The second generation was called BiCEP 2. Same concept, refracting telescope, same location, same optic. Everything was the same, except it had 6 times more detectors. And they were different type. They were superconductors.
It's like a BiCEP scaling law.
Yeah, exactly. That's right. Yeah. So we did that. Now they're on BiCEP, the 4th generation of BiCEP. So it's
like a new iPhone model, new BiCEP model.
New BiCEP. That's right.
Next season.
One last thing.
Except each copy is handmade and costs millions of dollars. And I came up with the acronym. So the acronym stands for Background Imager of Cosmic Extragalactic Polarization. It's kind of ironic because we ended up measuring galactic polarization, not extragalactic polarization. But be that as it may, we got funding for it, we upgraded it, and then eventually we did detect it. We detected the signal that would be revealing, indicative of gravitational waves. The only way the gravitational waves could get there is if the universe underwent a very brief period, but extremely energetic, incomprehensibly powerful expansion called inflation. This was predicted by Alan Guth, now at MIT, but at the time he was at Stanford also, almost getting fired himself, but then avoiding it and having a much better career than I had. But he ended up predicting this, and we realized that there would be signature of the relic gravitational waves from inflation, and that would imprint the CMB, and we discovered it, and the pattern that it would imprint would be a swirling, so the polarization looks like little sticks.
Do you have an image to show?
In my book, I do, yeah. In the book, you can show the image of the book, where it shows not the intensity, like the color on that plush little animal toy over there, but it shows little sticks. So the polarization is an orientation. It's photons are spin 1, so they have 2 different orientations, but you can't tell if the electric field's going vertically up or vertically down. You just know the plane of polarization. Like a rope, if you see 2 people shaking a rope, you can't tell, did it start going up or did it start going down? If you look away for it, you can't tell. So we only know the orientation. So at each point on the sky, in addition to the color, meaning the intensity and the frequency, we have an orientation of a stick. And the stick pattern, if they're gravitational waves, would form this swirling pattern called curl mode polarization. So at the gym, I realized you do curls at the gym, right?
That's
you know what I'm talking about. You know
what
I'm talking about, right? So that's why I called it BiCEP.
Curls, like for me, it's derivatives. Like
That's named after the bicep. That's very
That's right.
That's
so
pretty
it's
funny.
a muscle that does curls, right? So people like that name. And then we upgraded it, but we always thought, we detect it, we have to go back and see if it's really real. It has to be confirmed. Unfortunately, tragically, in 2010, the couple of weeks after we had deployed the second generation of BiCEP, Andrew Lang, who's my hero, my mentor, like a father figure to me, he committed suicide. So he died in Pasadena. He took his own life at a motel that was the same motel that he had put me up when I stayed to do the job interview 10 years earlier. I mean, it was an incredible kind of coincidence and confluence of events. But one of the things that happened after his death is that there was like a leadership vacuum, and the team of people, some of whom I had hired as, when I was advising Andrew before I left Caltech to come here to UCSD in 2004, they took over the leadership because they were there. I was still one of the co-investigators, co-leaders of it, and the founder of the BiCEP series of projects. But they had convinced themselves they didn't need me around anymore. And when they made the detection, I was part of the team and on the paper, and I helped with some of the results, and I had students working on it. But they did not include me in the big press conference and the big, newspaper articles that were written about it. And in hindsight, it was a great blessing for me because it turned out to, spoiler alert, not win the Nobel Prize. I realized I would not win the Nobel Prize like the night that it came out, right before we were going to publish it. Either they would win it and they kick me out and only 3 people can win the Nobel Prize at most, or we were wrong, which is kind of what I was leaning towards, and I kind of wanted to distance it from that at that point. And that's what ended up happening. We saw these micrometeorites that made the same curling pattern of microwave polarization. And we never, really had ways to validate it to make sure we didn't make a mistake, but we kind of let our excitement go ahead and we published it without peer review. We had a press conference, like I said, a very unorthodox way to approach it. But they were worried about being, scooped out of the discovery by the Planck satellite and others, and then losing their Nobel Prize.
Maybe if you can detail a little bit. I'm just curious, how many of layers of data processing was like before raw data to the final results of showing?
Yeah, so these detectors are superconductors. So what happens is that there are 256 of them for each polarization state. So there's 512 total. Each one either measures vertical or horizontal polarization at one different pixel, like a CCD camera. But it's tiny fraction of its modern CCD camera. It's 512 by 512. It's minuscule. But the pixels are big, and they have to be the size of the wavelength of photons, which is about 2 millimeters wavelength. So that's how you design the sensors. If you made them the size of an iPhone, it wouldn't work. You wouldn't detect anything. And they have to operate at 0.2, 0.3 Kelvin. And so we had to cool them down using these different isotopes of helium, called helium-3, to get down below, way below the temperature of the CMB even, let alone the South Pole. So we did all that, and what happens is they get a voltage out. And then that voltage, superconductors have low resistance. It's very hard to read out a sensor that has very low impedance. So you have to transform the impedance and make it higher impedance, then you can put it into a normal transistor amplifier. If you imagine you're trying to read out like 0 ohms, like with just sending in a current, it's almost impossible to do that. So what instead?
A squid?
We use a squid, exactly. Yeah. So we use one of these another type of superconductor called superconducting quantum interference device that modulates the flux, and that creates a higher impedance signal that can be amplified later by ordinary transistor amplifiers, which are cheap compared to the squid amplifiers, which are very expensive. And so each one of those detectors can be read out, or you can multiplex them. So you get many detectors are read out by a single squid, which is how we do things in the Simons Observatory. And then they have to get out to room temperature somehow after amplification, and then get amplified again and again and again. And then the sampling is about 100 hertz, not crazy. But now with tens of thousands of detectors at 100 hertz, we're getting close to a terabyte per day with the Simons Observatory. And that's raw data, and we keep all the data as we can. Even if we can't use it, we still keep it. Unlike CERN. CERN might have 12 events. The detection of the Higgs, I forgot how many events it was. It was like
10 to the 15th?
Oh, I mean, total events, but no, the actual number of Higgs bosons that they created was under 20 or something like that. So that means they threw out 10 to the 15th, basically, the difference between a millionaire and a billionaire is about a billion, right? So the difference between 12 and 10 to the 15th is 10 to the 15th. So looking at it's a very different type of data analysis. They trigger, we don't trigger, we just take all the data. And so by the end of the season, you'll make a map, you'll make an image just like the beach ball. How we do that, we have to filter, we have to do pointing, reconstruction, where it's looking, calibration. And it's very challenging to do polarization because there's no standard candle for polarization. There's no analog of a white dwarf that we know exactly what its mass is when it blows up in the case of the supernova measurements. Or, we can't make a fake signal and put it in the sky that has the properties of the CMB. It's impossible. And in fact, there's a lot of contamination. Starlink, SpaceX is exactly in the frequency that we're going to look at. So all these reasons mean it's very hard to calibrate the data. You look for all the ways you could have done wrong, systematic errors. You clean it as best as possible. Then you have to compare it to sources of astrophysical data, but not cosmological data, like the galaxy dust. That's an honest-to-goodness signal. It's not like they made a mistake and we didn't really measure something in space. No, it was really in space. It just wasn't from the Big Bang. It was from our galaxy.
So do you overlay it with CMB data? Or?
Well, we take, it is CMB data. So we take this.
in addition to previously measured one.
We will compare it to other instruments, but each new instrument is more sensitive than basically all the other instruments that came before it. So there's only so much we can get from that. In the case of BiCEP 2, yes, we did use the Planck data, which is kind of contemporaneous. And they had
a slide.
What's that? Yeah, the slide. slide. Yeah, I talk about that in the book. But mainly it was because we lacked frequency coverage. Remember I said there's 3 properties of light: spectrum, intensity, and polarization. We measured the polarization and we measured the intensity, but we only had one frequency, so we couldn't measure two sources of potential signal. So we had to rely on other sources. So we either used a picture of an image of a slide that someone had given from the Planck team, or made up models from other sources, but we couldn't do it internally. And that was a big gap, and that was partially why they thought that, oh, maybe Planck will scoop us and make the detection and win the Nobel Prize that we would have won if we had been a little quicker on the draw. But a lot of it, I feel, traces back, personally to the fact that Andrew wasn't there anymore, and he wasn't really kind of the all-knowing, hero guru, whatever you want to call him, that could give the gravitas to take a step back from the edge before we went forward. But in the end, thankfully, or depending on how you look at it, because of BiCEP, we were able to build the Simons Observatory, which is now operating, and we'll be able to do everything that the BiCEP team has done and continues to do. They're still working on it, but it will do so with more sensitivity, higher frequency coverage, better angular resolution from our companion 6-meter telescope. So the kind of death of BiCEP, for me personally, I'm no longer affiliated with it, led to me 100% committing to the Simons Observatory, which has got the power to really be maybe the last of its kind, the biggest experiment ever funded to do this type of research.
And there's an assumption that the quantum fluctuations during the inflation cause the polarization of the light. Is that right?
The model is that, and this is one of my great mentors, Alexander Polnareff, who's now retired from Queen Mary, but when he was working for the former Soviet Union, they were, there's this whole group of astrophysicists who were working partially on astrophysics and partially on the Soviet atomic bomb, because they had a lot of things in common, including, these high temperatures, high pressures, fusion, all these processes. So we were able to kind of leverage their expertise, and sometimes the, higher powers at the universities that they work with would let them dabble in cosmology. And when they did, they came up with these great ideas. One of the ideas was that if the universe began with this inflationary epoch, it would produce waves of gravity. The waves of gravity aren't unique, but they have a unique feature in that a wave of gravity, if it goes through this room, would make us weigh less or more by a minuscule, amount less than 10/19th of our mass fractionally. But the other thing it does is it actually shears space-time. It can actually make space-time on successive crests and troughs shear, and that's what causes the twisting, curling pattern in the microwaves. So the logical syllogism that we are following here is, if you measure this pattern of curling, swirling microwave polarization, the only way it could get there over the entire sky would be if it occurred extremely early in the universe's past, and if inflation took place to cause the universe to expand. And what we're effectively seeing, these gravitational waves, are actually amplified quantum fluctuations in a scalar field called the inflaton. Those quantum fluctuations then get magnified by the expansion to be very large-scale signals. Now they're degrees across. Remember I said we only have to see a few degrees. We don't have to see nano arc seconds or anything like that. So the gravitational waves come from inflation in this idea, but inflation is not, again, you can't prove inflation, but you can get a lot of circumstantial evidence for it. So imagine the gravitational waves from LIGO. Those were produced from a single pair of black holes, 30 times the mass of the sun. But imagine every black hole, every galaxy, every supercloud, everything exploding, from a quantum field, but literally times a trillion. Now, the caveat is that occurred so long ago that the energy is diluted and expanded by the universe. Is expansion factor by a factor of the redshift to the fourth power. That's how radiation dilutes.
Why do you need to assume a quantum fluctuation versus just like thermal randomness? Like there's thermodynamically, you're going to have some differences in density and so on.
So when we look at the CMB, we're seeing the last scattering of photons from tightly coupled plasma. So the plasma is photons, electrons, and protons. The photons are scattering off the electrons. They only scatter off unbound electrons. When the CMB and the temperature of the universe cools below the ionization binding energy of hydrogen, the electrons are no longer free to scatter. At that point, you get a snapshot of what life was like in the early universe. And at that time, it was a plasma. That's all there was. There was gravity and gravitational waves, but they are far subdominant to the ordinary fluctuations of matter, temperature, pressure and what are called acoustic oscillations. They're basically sound waves. Sound waves in a plasma travel at the speed of light divided by the square root of 3 in this type of plasma. And the density fluctuations in them come from the excess of basically dark matter. So the pattern there is really tracing the pattern of dark matter establishing a gravitational potential well, into which ordinary matter falls into that you can see. If it was just dark matter, we wouldn't exist and we couldn't see anything. The ordinary matter falls into these gravitational wells. It drags with it photons, and you see that imprint of the photons. The other thing, though, that's happening is that these waves of gravity are present. They are causing the space-time to shear as seen from a given electron before it scatters. So they see a little bit hotter radiation coming in one direction, and then below them they see hotter in this direction. So they get this shearing, twisting pattern. That causes a polarization of the photons to then have this pattern that comes out to be like a curl, a whirlpool, and that will be associated with a single set of perturbations. And then you have to superimpose all the different gravitational waves that could have been present from there. So the only way you can get the curling pattern, you're right, is from gravitational waves. But every other all that is fluctuations that have nothing to do with gravitational waves and everything to do with plasma sound waves in the early universe.
But then why is it always said that there's like a quantum, like the reason that the universe isn't uniform is there's the quantum fluctuations. So why aren't the classical fluctuations sufficient?
So you have to ask, why did the dark matter form where it did? So the dark matter can only form if there's a place that breaks the symmetry of space-time curvature. That's like the sun is formed where it did because there was a previous star that was here. Why that previous star formed here? Because there was other stars there. Why did our galaxy form where it did? Because there was actually an excess of dark matter here. And that dark matter established a gravitational potential well, into which gravity will pull in ordinary matter, and eventually you'll get hydrogen fusion into helium, and then you get planets and people and podcasts and everything else, right? Those types of fluctuations exist. Those are created, the perturbations in the space-time curvature. That's what's coming from inflation. If you don't have inflation, you have to explain why there are fluctuations at all. And why wasn't the universe perfectly homogeneous, smooth, and perfect? Why would there be any place to tell dark matter to form there and not here? And so what inflation does is it gives a seed mechanism for planting tiny seeds of pure curvature into which gravity will pull into, curvatures is another way to say gravitational potential, so into which will fall ordinary matter. So the paradigm that we see now is consistent with those fluctuations in curvature, but it's not as good a piece of evidence as it would be if we see the gravitational waves. Those can only be produced. In other words, there are other models that produce the sound wave plasma fluctuations, but don't produce gravitational waves. But so therefore, if you see gravitational waves, you don't prove inflation, but you disprove everything else, which is as good as you can do in science.
Are there any byproducts on measuring the polarization? So I understand the first goal is to study the primordial gravitational waves, but do we get also information about other things?
Yeah, so not necessarily from the BiCEP-sized telescopes of the BiCEP or the what we call small aperture telescopes of the Simons Observatory. Those are designed only to look for galactic contamination and the curl pattern from inflationary primordial perturbations. But the big telescope, 6 meters across, can see a whole bunch of other stuff. It can see all the fine scale details, much higher resolution, better sensitivity than the Planck satellite even, which is $1 billion project or more. And it can look in particular for a host of other astrophysical phenomena, formation of galaxies, of clusters of galaxies. It can also tell us about things that emit heat, anything that emits heat. So asteroids, Planet 9, we could potentially detect the 9th planet using a cosmology experiment, because anything that exists that has mass, that is made of matter, is going to give off heat. So we can measure that. We also are very hopeful. We can measure, we know neutrinos have mass, but we don't know what the mass is. So we're hopeful we can measure the mass of neutrinos by using the fluctuation pattern of the cosmic microwave background and its polarization that will tell us about the size of the gravitational potential wells that are associated with the neutrinos. And that's another way of indirectly measuring their mass. We can't measure them in the lab directly what their mass is. It's very difficult because they're so light and they don't interact very much. But if you use the cosmos as a laboratory, it's much more probable that we can actually detect that. So there's many different aspects of cosmology, of astrophysics, of particle physics that we are uniquely capable of measuring, and now we just have to collect enough data to do it. We just got first light. We got first light last year on the first of the small aperture telescopes that are looking for these gravitational waves, and we got first light of the large telescope that can detect all these other things. Anything that's not gravitational waves can detect all of those things. We just got first light with that in February, so 3 months ago. And now we're just going to turn loose and hopefully, have enough data in the next 4 years to really detect or set limits on all these different phenomena.
Would there be any benefit to having a space-based telescope for this purpose specifically? Would that be your dream to have your own satellite?
There are even plans to do it. The problem is anything in space is 100 times more expensive. And this is already, so that would be the cost of the James Webb Space Telescope just to do this. And the Webb telescope is the same size. The primary mirror is the same size as our telescope. Yes, it would be better. Each detector would be 100 times more sensitive, but there are a lot of limitations. Like the Webb telescope, you remember, and that actually 3D printed by one of my students, actually folds apart. So there was a limit. You couldn't get into a rocket without that. For the measurement of the gravitational waves, you actually don't need to be in space. It would be better, but it would be more reasonable to do it cost-wise. But you're kind of putting all your eggs in one basket. You don't need a giant telescope in space. You just need like a lot of smaller telescopes in space potentially. But given the budget environment right now, and the fact that you can do it from the ground is more promising than most other sources where you need to go into space.
What are the main atmospheric contaminants? Just water vapor?
Well, there's anything that has molecular absorption or emission band. Water vapor is really bad. That's why we go to space, or we go to high mountaintops or the South Pole. So right now in San Diego,
can you get better data if you induce rain to get rid of the water? And then
actually, you gave me a good idea. Our competitors
can we
seed the clouds over them. Yeah. Thank you, Mike. That's
you
great.
You can delay it. Oh yeah, you could do it that way. You could delay it.
No. So anyone who's heated up, coffee in a microwave, realize that water absorbs microwaves.
Which is a crime, by the way.
So if you have a photon that's been traveling for 13.8 billion years, the last thing you want is for it to get absorbed in the Earth's atmosphere. So going to space is very expensive. People have done it. So you want to go somewhere dry. You want to go to a desert. Most people don't think of the South Pole as a desert, but it's one of the driest deserts on Earth. So right here in San Diego, which is also a desert, or it's called a coastal desert, if you were to take a glass, any width, it doesn't matter, and extend it to space, and then cool it down to below the dew point of all the water, all the vapor that's suspended above you in this jar, right now we would condense about 2 inches of water, 1.5 inches, 2 inches of water, even in a desert. That's not how much water vapor is going to rain down on us, but it's the column density of water. Yeah, so it's there. The South Pole, it's about 1/3 of a millimeter. So it's 100 times better, at least. And Chile is about 1 millimeter. Chile, you can get to tomorrow night if you wanted to. You could be there in 25 hours if you wanted to. And you can drive up to the mountaintop, sea level to 18,000 feet almost. You have to wear oxygen. You're above half the sea level pressure. You don't have enough oxygen to think clearly, so you have to wear cannulas, hard hats, ultraviolet radiation layering down on you. So so when we look at the CMB from there, we're above a lot of these water vapor contaminants. The other type of thing that you can't get rid of on Earth is oxygen has emission and absorption features that we can see. That's basically it. Oxygen and water vapor, nothing else. And the atmosphere is kind of God or whoever you like, in Mother Nature. They put bands, where we get enough photons that we can get good statistics on. And where we get high absorption or high emission, we just don't put our frequency, we put our filters around those so we don't see into them.
So, you've obviously given a lot of thought to the Nobel Prize, right? Like we don't have to go into it here, but that's something you've opined on, in the book, in other places. So if you had to do kind of like a venture, like a startup to win the Nobel Prize, right? And you could hire 5 teams to work on 5 problems for 5 years, which problem areas would you focus on?
I mean, right now I am focused on a project that, if successful, is in that level. And so what I like to do now, my research portfolio has to be balanced. It can't be like Bitcoin, nothing but Bitcoin. You can have a little Bitcoin if you like, but you should have something, S&P 500 index fund. So that's why what I love about the Simons Observatory and my colleagues like Mark Devlin and Suzanne Staggs and Lyman Page and Adrian Lee, all these other great scientists, Jeffrey McMahon, is that they are so good at doing all the things that we can do Planet 9. We can look for galaxy clusters. We can look for neutrinos. So it's a balanced portfolio. We know all those exist, right? We know neutrinos exist. We know dark matter exists. We know the galaxies exist. So there's guaranteed science. Like the S&P is going to go up 8% per year. So, and then you have your Bitcoin or your, fart coin or whatever you want. You have your speculative venture. For me, that's looking for this signal from inflation. We don't know if it took place. Inflation could have taken place and we could never see it because the energy scale is too low. Or it couldn't have taken place and we never see it anyway. The next kind of obsession that I have now involves also high risk, but also balanced portfolio. It's called Chern-Simons cosmic birefringence. It's a lot of words to it. But the Simons and Chern-Simons, suffice it to say, is the same Simons as the Simons Observatory. Jim Simons, my late great mentor, another father figure for me. And it's the following. When polarization propagates through materials, depending on the type of material, the polarization orientation can rotate, you still have oscillation in a plane, you still have linear polarization or circular polarization, but the plane in which it oscillates in will change. If that's true, something completely bizarre would happen in our universe. We have not tested this on very, very distant scales. It's very difficult to test this. You need very sensitive detectors, very high quality optics, and multiple frequency coverage. So we've only been able to really think about doing this accurately with the Simons Observatory because the way to calibrate these instruments is very difficult to do. So at the Simons Observatory, we're using drones. So we're using a drone with a polarized source on it. That polarized source, technical reasons, can't fly into the distant far field of our big telescope. It's too high up. Drones don't work very well unless you have like a Global Hawk or, the Predator drones or whatever, which, we've tried to get actually, but they won't let us use it. So one of the teams that you give me money to hire would be building a satellite. And that satellite would not look out, it would look down. And it would broadcast 100% known polarized signal at all frequencies, all times of the day when it's over us. Perfect point source, perfectly calibrated, standardized to NIST, cesium clock, everything you could possibly want on it. Probably $20, $30 million, but money's no object, so I shouldn't even think about the price, right? Another thing I would do is build, and that would be calibrating all these instruments. Making an artificial, like a laser guide star, that would be also another thing. And that would shine, again, these are calibration. Most people don't realize in science, we don't get paid to make these detections. We get paid to remove the unwanted stuff that we detected by accident. That's called systematic errors. Systematic errors cannot be removed by taking more data. If you have a ruler and it's 3 centimeters too short, it doesn't matter if you measure this table 1,000 times, you'll never get it right. You need something to calibrate against that known length, the wavelength of a cesium atom times the speed, whatever. Then you could do it, but you can't do it unless you calibrate. So the hard part about being a scientist is not making the measurement really, it's calibrating the data and getting rid of systematic errors. So everything that I want to do at first would be calibrate and get precise measurements of these things. Next thing would be a real long shot, but to get out of the plane of the solar system with a CMB satellite in space and moving at extremely high velocities, get above the scale height of the galaxy. Might take a little while, but maybe we could do it. Yuri Milner, gives me a couple tens of billions of dollars. So that'd be one thing. Get rid of a lot of the dust in their solar system and in our galaxy, and that's most of the background that we would care about to worry about. Another project, I forget how many we're up to, maybe 3 or 4, would be huge optical telescopes in space. And that would be polarization sensitive. There's never been a polarization sensitive optical telescope.
Have you heard of the idea of making the Earth into a telescope where you use the refraction of the atmosphere?
Yeah, my friend David Kipping and others have talked about that. Yeah, Earthscope or whatever. That wouldn't necessarily exactly do what I wanted to do, but yes, that's a very cool idea. What I'd want is like, a bunch of, Hubbles and James Webbs and even bigger things, 30-meter telescopes in space. Because when you look at something in a type of way that no one's ever looked, Galileo optically looking at the sky, Herschel looking infrared, eventually, and then gravitational waves opening up this whole new vista for astronomy. You get incredible, new discoveries. No one's ever looked with a telescope at all different wavelengths in space that's polarized, that's dedicated to polarization. And then I'll show you when we're done with the interview, I'll show you some of the initial steps for building a prototype here to do that, but it's in San Diego, it's not in space. But until your check clears, that's the best, or my fart coin cashes out. That's about as good as we can do. And then telescopes on the moon are always fun to think about. And then, particle accelerators, the size of the solar system and beyond are always fun to think about. With your money, anything's possible.
This just made me appreciate our ability to inject calibration lines.
Yes.
In LIGO so much more.
Yeah.
'Cause that's just like
if you
a
guys
button.
didn't do that, you wouldn't have been able to do what you did. It's absolutely true.
Yeah, but we don't need extra.
But notice
we don't need an extra.
I didn't say I need a team of theorists, right? I didn't say I need all these brilliant theorists. I think that's something that gets overlooked. Even in what I do outside of work, which is my podcast, right? There are many more people that Sean Carroll and Brian Greene, Jana Levin, people that have podcasts that do stuff. That they're all theorists. Michio Kaku. I don't know of another experimental physicist. David Kipping is an observational astronomer, but doing really looking at what does it take to actually get the data that these brilliant theorists will then use to either claim they're correct or claim they're incorrect. These are just some of the most fascinating things, and it gets to tinker with your hands and not just sit in front of a pad and paper all day long. So I think we have too much theory, and I don't think we have enough experiment right now.
Oh, I would totally agree.
Yeah.
It's just much harder. It's same as maybe hardware and then software.
Exactly, yeah. I always say that to my friends and listeners in the audience that are software engineers. Why do you have to make fun of it? Without software engineering, you'd be screwed. Yeah, I mean, there's a lot of really interesting. I'm fascinated with AI now and using it all the time. And I hate it when I ask my students, do your professors let you use AI? And they're like, no, it's forbidden. I'm like, that's one of the dumbest. It's basically like child abuse. I even taught my daughter, as third grade, how to use AI. She made a song about, with her name in it, and you could exclude oh, I don't want Dua Lipa, but I do want, whatever. She likes little girl stuff, right? And she learned how to prompt age 9. It's incredible. And to think that imagine a teacher saying you can't use it. It's oh, you can't use a spreadsheet when it came out, or can't use Fortran, or you guys probably didn't use Fortran, but IDL or C, or imagine not using Python. I mean, it's ridiculous. So I want them to embrace it. I want them to be using it and we actually did a test with it. This is one of the things that the only kind of research I've done with AI. I asked the following question: Einstein, imagine you gave Einstein AI in 1914, before he came out with the theory of general relativity, and you said, here's the data, here's the orbit of the planet Mercury, and which he knew about, put it into AI, and then tell me what comes out of the AI. Does it predict the bending of space-time due to the presence of stress energy in the form of matter? Can it derive that? I know it can predict. I mean, I've debated with Max Tegmark. I know it can solve the orbits perfectly, but can it predict that you need to go from, vectorized data into Riemannian curvature? It's such a leap of human intuition. And I almost know that it couldn't do it because we tried to do it. And what it did is said it had to discretize and make on a grid. And it could reproduce the orbits, but it didn't come up with things like the Ricci curvature, the Ricci scalar. It didn't come up with Riemann tensor. It didn't do any of that. It's just, here's a brute force method. So in other words, it wouldn't have come up with the idea. It's like if you gave it, here's a list of all these people that have died recently. You gave it to it in 1862. Is it going to come up with the germ theory of disease? Oh, maybe there's some germ. No, it would never be able to do that because that's something that's observational. And that's, again, experimental, calibrational. You need to relate it to something that is uniquely the domain of humans. And the last thing I'll say about it is Einstein himself said, the happiest thought of his life was that if he was on an elevator, it's kind of weird, and the elevator cable broke, he'd experience no gravitational field. And that's called the Einstein equivalence principle. So how could is Claude 24 going to be able to feel what it's like to have an elevator cable break or have I'm really happy. if my AI gets happy, something's going wrong.
Someone needs to prompt in.
Yeah, but I think partnering with AI is very powerful. And the mathematicians are doing this, but things where there's proof, but where there's not proof, I think they get very uncomfortable. And as I said many times throughout the conversation, you can't prove something in experimental science. You can just observe it and exclude or disprove other things that could have been true but aren't.
But what's your opinion on falsifiability? Is that like the basis for a scientific theory?
I don't think it's the only criterion. It's kind of outdated in some ways. I do think it's at least, maybe necessary is too strong a word, but it's certainly not sufficient. I mean, I can tell you that, I read my horoscope today, as I do every day, and it predicted what would happen. And, and it didn't happen. I got the parking space in the garage that you guys were trying to get. So it was false, right? So is astrology science? I mean, that would prove that it is, right? And of course, it's ironic because Popper used astrology as one of the many reasons to think that it's pseudoscience, but it's ironic because it's actually falsifiable.
Yeah, I think one question that kind of we can cut it out if you don't want to discuss it, but I think it's just an interesting question. Is so the book had a lot of feedback, or ideas how to potentially improve the Nobel Prize, right? Because the Nobel Prize, again, it's just one of the prizes and so on, but it does have all these downstream effects. Like even in my world, like I work in startups, and people get like a Nobel Prize winner on their advisory board, and does that person really get involved? Who knows? But it's like basically a quick way for someone to say, oh, you got a Nobel Prize winner involved, so this must be at least sensible, right?
It's the ultimate stamp of approval.
So the question is then, okay, having written this book, that's kind of, it's been, I guess, 7 years or so. Have you actually had any kind of traction with like interacting with the people who run the Nobel Prize, or even getting any feedback on your ideas about like improving it?
Initially I did. I mean, everything has an exponential decay curve to it, right? So first year, now you say 7 years, it makes me feel really old because I remember writing it, 10 years ago before I had some kids that I now have. So it kind of dates a period in my life. And truth be told, it's something I was obsessed with as a kid and a postdoc and a graduate student. And I almost never think about it now. I have been asked once, I was shocked. I got the letter to nominate a second time. So in the book, I talk about the first time I was asked to nominate and how I took it as a homework assignment, to kind of rehabilitate or redeem what Alfred Nobel really wanted. He said it should go to one person who came up with an invention last year that had the greatest benefit to mankind. And now it's 3 people can win it for stuff they did 20 years ago, 50 years ago, and who knows if it has a benefit to mankind. Abstractly, did the lighthouse have a huge benefit to mankind? At that time it did, but it's certainly not like LIGO or something else. And interestingly enough, I've talked to, Barry Barish wrote the foreword to my second book, and he complains about a lot of the stuff that I complained about, but no one's ever refused the Nobel Prize. And no one's ever, said, well, I think I'm going to take my Nobel Prize. And the LIGO team, many of whom contacted me throughout the writing and post-writing the book, saying, I should have done it. I should have, they didn't take the prize and cut it into 1,000 pieces. They could have. I mean, the degree to which the scientific community worships the Nobel Prize and they cultivate that as a monopoly is the thing that most surprised me about it. Just how criticizing it otherwise atheistic people like Sean Carroll, if I criticized it, oh no, it has all these great features and it's wonderful. And even though he wrote, a blurb for the book, a lot of people just, Sabina Hassenfeld or another person, they think it's great. And they think, yes, it has some problems, but nobody thinks about changing it, reforming it, what could be done to it. So I think a lot of it, every single right sitting in this chair, Adam Rees was here last year. And he said, yeah, it should go to everybody on the team. And I'm like, well, did you give yours back? Can you get a piece of it to your friend, at the University of Texas who deserves it, And they never do. Even Feynman, Feynman claimed that, he didn't care about it. He wasn't going to go to the ceremony and pick it up. Supposedly he drilled a hole in it to where it has a big chain around his neck. Nobody can prove that. I don't think that's true at all. But, he would say things like, I did it, despite the Nobel Prize, I don't want to be a member of this club. And then, but he kept his Nobel Prize and he would refer to it, right?
Is it like actually a time maybe to create like a new system? Because it reminds me, it's like, maybe people who work in like industry with like Jira tickets, like to move the progress. And then people start to abuse it in some sense. So it's like, they're not really like working on the progress, but they're working to satisfy and move all this like the jury tickets game. So would like the Nobel Prize turn into maybe originally, since maybe like the first Nobel Prizes, they were kind of satisfying, the kind of awarding the big breakthroughs in science, and then it turned out into something else. So do you have any like suggestions of use? What would be like the new way of kind of stimulating the breakthroughs in science and technology?
Look, I mean, I think, the goal in writing it wasn't to tear it down and destroy it. It was to reform it. I don't think there's anything irredeemable about it that couldn't be fixed without, some attention to detail. The last time the rules were rewritten again was 1974, like 50 plus years ago. And that was to like allow or to forbid posthumous awarding of the Nobel Prize. That was one of the things. So like anything that doesn't change, that's changed once in its history, officially. And remember, they changed it unofficially a couple of years after Alfred Nobel died. They gave it to 3 people, like Marie Curie and her husband, and I always forget the third. It wasn't Becquerel, but anyway, the point is, it can be reformed, and it should be. If they want that, my whole point in the discussion of the Nobel Prize was only 3 chapters out of 11. It's not really about that. It's more a memoir, being a scientist. But it was to like, let's save the Nobel Prize before it's too late. Because all these other prizes, they're talking about the Pulitzer Prize. Nobody cares about the Pulitzer Prize anymore. I mean, if you're in writing, maybe you do a newspaper, but nobody really cares about it. These things don't, but it used to be much more prestigious than the Nobel Prize for a long time. And now, there are other prizes, the breakthrough prizes, people don't really associate. Templeton Prize was established explicitly to be worth more money than a Nobel Prize because it was about religion, spirituality, and the sciences harmonization. And Sir John Templeton, wanted to make the money equal or better than the Nobel Prize. So all these spin-off things have come about. Jim Simons was asked to invest their portfolio I think it was in the 1990s. He was an unpaid financial advisor to the Nobel Prize Committee. So they obviously care about it. They want to keep it going. So some of this could be made for reform so that they don't get, Me Too'd or, they don't have.
What's the one change? If you made one change, what would it be?
I think the exclusion of teams is the biggest flaw and the biggest contradiction between how science is done now versus 1900. That, teams of 1,000 people are needed, more. The Higgs boson, went to 3 people, Brown and Englert, and Higgs, and that rewrote, people like my graduate school group theory professor Jerry Guralnick, totally out of history.
But let's say if I have 5 minutes to decide who to have like control a bunch of funding, and I'm using the Nobel Prize to make that decision, and you give it to 2,000 people, what am I supposed to do?
Well, no, I mean, there's always.
I'm just saying, doesn't that reduce the social utility of it? If the social utility is to like single out some people and kind of arbitrarily give them some if you're, sway in society,
as long as you're not afraid of a
like
little
scientific
work,
society.
I mean, let's say it went into this building right now. They said, we're going to drop a Nobel Prize on everyone in this building. Do you think it would be really hard to figure out that like you probably won it because you're in the building, not because you did any of the work that was actually related to what my colleague upstairs discovered, life on an extrasolar planet? I mean, this is something that we could debate, but in science, I mean, there's always a hierarchy. Okay, so students work on it, they get to claim a Nobel Prize, that they have it, maybe they win $50 or whatever it comes out to be. I think that would encourage more scientifically to be able to say things like that. That's what happened with the climate, with the IPCC Nobel Peace Prize. There were physicists on that are Nobel Prize winners because they won the Nobel Peace Prize because they're part of this intergovernmental panel. So I don't think it would diminish. They claim it. Al Gore, claims it. And I think, more than that, I mean, I would be more worried about the irrelevancy of the Nobel Prize in the future. People aren't going to care. Or there'll be somebody who says, look, you can have a Nobel Prize, but if you do, you won't get this $1 billion. I mean, it could happen. Like some super billionaire could say, I want only stuff. Let's say Musk, completely took over all of science in America and just uses his whole fortune and says, the only thing U.S. should do is go to Mars. I don't think that's a smart thing to do, but he could do that. And then there would be enough of a disruption to, if he paid every single professor in this department $1 billion to work nothing but Mars, you don't think they would do it because they care so much about, detecting some molecule on some other planet? Maybe those that hate him would do that. They wouldn't take his money. But I think, if you paid a person enough money, even a scientist, they would say that. So I think And then what would happen to the Nobel Prize? It would be for going to Mars. So I think if the Nobel Prize doesn't cultivate the essence and the core of what it means to do science and what makes us uniquely capable of doing science as human beings, operating teams and building instrumentation and pushing the boundaries, I think it may be at risk of being irrelevant. Again, it's kind of like my hope that it survives, not that it goes away and I want to kill it.
Maybe in the last few minutes, do you want to talk about the Lorentz invariance?
I do, but I'd rather show you it. I'd rather show it to you.
Yeah,
before.
maybe we just usually have a closing question. I don't know if you want to.
Sure. Do you have any advice for younger scientists, maybe studying PhD students?
Yeah, I definitely do. So I wrote my second and upcoming third book, Into the Impossible. That one's called, if you want to pick that up, show it again. So that one's subtitle is Think Like a Nobel Prize Winner. And this was written, and the next one's called Focus Like a Nobel Prize Winner. That comes out in September.
This is really like optimizing.
This is my
for Amazon sales.
This is my brand, right?
Selling the books.
When you got a winning brand, and it's like one of my friends said, asked me, well, who are you competing against? And I was like, science books. And he's like, yeah, you idiot, you're competing against like every single Oprah and Michelle Obama and Taylor Swift and cat video that ever has been made. So this is a book written after I did 9 interviews with Nobel Prize winners, and the second one's written after the second batch of 9 Nobel Prize winners. Someday I've interviewed 21 so far. Maybe I'll do a third one, but I'm kind of, doubtful. I'm writing another book about Lorentz invariance and other things. So who knows when that'll come out. But every time I interview 9 people, I take all their wisdom, not just their knowledge. Anyone can look up what they won the Nobel Prize for, but what specific wisdom do they have, literally, for a young person, their 20-year-old self. And I asked them, what would you do, go back in time, and how would you handle the struggles that you had to give you the courage to go into the impossible and do this thing that almost no one in their right mind would say yes. Only one of the people in that book said, yes, I knew I was going to win a Nobel Prize and I deserved it and I should have given it to me sooner. I won't say who that is because I don't want to embarrass him. And in the next edition, I have people like Donna Strickland, you guys will probably love, the lasers aficionados that you guys are. And, she's just so humanizing of what a scientist is and what it takes to succeed. It's not just raw brain power. It's collaboration. Sometimes knowing who to collaborate with in the competition. Remember I said it's more important who you work for and work with than it is what you work on. You could work on the hottest subject. Today it's AI. Who knows? Who cares? If you don't get along with your advisor, if you're working with cutthroat people that are your competitors, and that happens a lot in science, and people don't realize. They think scientists is just like children asking questions. No, it's very cutthroat. It's very demanding because there's only one Nobel Prize. It's the strongest monopoly ever created on Earth. So people that aspire to that rather than financial remuneration because they went into a field that doesn't pay as much, they went into it because they love science, but they also like recognition. So I think partially it would be to recognize that you have a life outside of science, and that most of what you do in life, your kind of identity should not be tied up with who you are in the laboratory, but it should be made up of things that give you excitement and enjoyment and relationships with people, and not with computers and AIs outside of the laboratory. And that's what's most enduring, and that's what leads to true happiness. And that's what the thread is between all these people, is the connections they have with other people, not with this just complete obsession with the science and nothing else. It's a story of individuals and challenges, and I wrote it to be applicable to a car salesman in Oklahoma as much as to an aspiring Nobel Prize winner. So read that book, and then September 9th comes Focus Like a Nobel Prize Winner, which is about really literally like how Donna Strickland would endure long winter nights in Canada, working on laser chirp pulse amplification, and how she did it and what made it, gave her the endurance to do it. So that's coming out in the fall, and 8 other people too.
Great, I think that's good.
Okay, Brian, thanks. This was
Thanks a lot.
Yes, thank you.
So,
Amazing conversation.
Let's go on a lab tour now. Let's take a lab
Let's do
tour.
that.